Welcome to this video on the vibronic funnel. Conical intersections, the exact regions where two electronic states of the same spin multiplicity become degenerate, rewrite photophysics by breaking the Born-Oppenheimer approximation. The breakdown of the Born-Oppenheimer approximation occurs when the adiabatic energies become nearly equal, causing non-adiabatic derivative couplings to grow massive. This means the coupled nuclear equations can no longer be separated. The quantum mathematics of the jump shows that as the energy gap shrinks toward zero, the non-adiabatic coupling blows up to infinity. This is the mathematical failure of adiabatic separation when eigenstates are hypersensitive to nuclear displacement. The intersection seam is not an isolated point, but a seam of 3n-8 dimensions. The branching plane is the 2D plane that lifts the degeneracy, spanned by the g vector for difference gradient and the h vector for derivative coupling. Conical intersections are topological objects, not just energetic crossings. They are defined by the exact degeneracy of two adiabatic states, divergent non-adiabatic couplings, and non-trivial topology through the molecular Berry phase. The mechanism of falling through the vibronic funnel involves 4 steps: vertical excitation, steepest descent toward the crossing point, non-adiabatic transfer at the seam, and finally, dumping heat into the ground state. It is important to distinguish between same-spin conical intersections, which drive internal conversion, and cross-spin minimum energy crossing points, which are governed by intersystem crossing and spin vibronic coupling. In organic emitters, brightness is a competition. A low-lying, easily accessible conical intersection, minimum energy conical intersection, MECI, acts as an efficient non-radiative trapdoor, leading to ultra-fast internal conversion and quenching the fluorescence. Aggregation-induced emission, or AIE, occurs when molecules are tightly packed in the solid state. This physical blocking of large amplitude torsion restricts access to the conical intersection, resulting in bright emission. In first principles computation, CAS-CF's CASPT2 is the gold standard for strong-state mixing. Spin-flip TDDFT is a scalable workhorse for large organics, while EOMCCADC serves as alternatives for excited-state crossings. The computational workflow for statics involves identifying bright states, mapping excited minima, locating the minimum energy conical intersection, or MECI, and analyzing the geometry to understand the nuclear mechanism. The second part of the workflow focuses on energetics and dynamics. This includes computing accessibility of the MECI, mapping competitors like singlet-triplet crossing points, and running non-adiabatic molecular dynamics, or NAMD. A checklist of deliverables for an emitter project includes vital energies, topologies, and geometries of key states, and environmental modifiers like solvent effects or crystal packing on conical intersection accessibility. Molecular design rules for suppressing quenching include rigidifying the scaffold, structural blocking, solid-state confinement to restrict motion, and deepening the trap by increasing the MECI energy barrier. The intertwined landscape means the molecule no longer moves on a single electronic surface. The vibronic funnel can be either a disaster for fluorescence or a highly tunable mechanistic lever, depending on molecular design.